Let's take on a slightly more challenging problem than we looked at in the previous video, where we introduced a really important technique for thinking about and solving problems using recursion. If you missed that video or skipped it for some reason, I would encourage following the link above to go check it out. So the problem we're going to be looking at in this video is can we determine whether or not two linked lists, singly linked lists, are equal to one another or not. So let's imagine one list A that has, like, say, I don't know, 110, followed by 210, followed by none. And I'm just gonna, these are node objects that we would think about in a linked list sense. I'm not gonna circle them and make them look like nodes to have the output look a little bit more consistent, like we'll see when we have string representations of these linked lists. But they are objects linked to one another. And then we might have something like 110, and then, you know, another, I'm just using some course numbers from UNC, 283, 455, where we might have a slightly longer list, right? And so if we ask, are these two are these two equal to one another? Is equal AB, right? If we imagine a function named is equal AB, we would expect false, right? No, these two lists are not equal to one another. So how can we determine whether or not two lists are equal to one another? Well, one way would be to think about this from the imperative side and start from the front and say, okay, well, how can we compare the first nodes and then move to the second node and then move to the third? And then, you know, the second node actually would have been enough to know that we weren't done. But let's not go down that road, not think about this sort of more complex solution, and let's apply the technique we learned in the previous video for starting from the simplest problems possible, right? So like we can imagine these are the lists we'd like to ultimately work towards being able to determine whether they're equal or not. But why don't we start with simpler lists first, right? So what if we imagine, what are the two simplest lists you can imagine coming into this? And in fact, this would be a great point to pause the video and try and come up with what are some of the simplest cases you can imagine that wouldn't involve any recursion at all. Cases that you could solve the problem having only two nodes from A and B and know whether or not they're equal. So go ahead and pause the video here and see if you can come up with the different cases that either you would know that two nodes or two lists are equal to one another without any recursion, with only one function call, no loops or anything like that, or that they're not equal, right? So if we think about the simplest case, we might think about a case where we're asking is equal. And I'm just going to write is eq for the purpose of this slide to shorthand a little bit. Is equal and none and none. So two empty lists. Is an empty list equal to another empty list? And this is, you know, philosophers might have things to say about this, but we're going to say, yeah, the empty list is equal to the empty list for our purposes, right? You could be pedantic and have long, really boring arguments about this, but no, we're going to call these two things equal for our purposes, all right? So that's easy. You have two empty lists. They are equal to one another. Our job's done. Well, all right, what other case could we imagine? Well, oftentimes it makes sense to try and permute, like just change one thing, keep one thing constant, change the other, and vice versa, right? So what if we permute and said, okay, well, what if our first list was like, say, 110 followed by, and then I'm not going to write out the rest of our list, right? We're just saying this is a non-empty node. We have a node that has some data in it, and we're waving our hands and saying it's 110, followed by none. Are these two lists equal to one another? No, like you've seen enough, right? You've reached the end of one list, but you've still got more nodes in the other list. So of course they're not equal to one another, right? So this would be false. And similarly, well, if we're covering this case, we should probably think about, well, what about in the opposite? So is equal. And we'll say the first one was empty and the second one was like, say, some empty list where we have a value. This would also be false, right? These are not equal to one another. One list, we've reached the end of it, and B, the second list, we haven't, right? So those two lists aren't equal to one another. All right, well, is there any other case where we know just looking at one node of each list without recursion, whether or not we're done? And yeah, there is one, right? If they're not equal to one another, so if we have something like is equal, and we can imagine, being at this point in the input list where we have like 1 is 210 followed by 283, or sorry, 210, and the second list is 283, right? The first list is actually 210 followed by none, and the second list would be 283 followed by 455 followed by none. But remember, we're processing one node of the linked list at a time. And again, we're using just pseudocode hand wavy notation here, and we're imagining these are the two nodes. Are these two lists equal to one another? No. As soon as you see at the same position two nodes that aren't equal to, whose data values aren't equal to one another, then we know that the lists aren't going to be equal, right? So that's going to be false as well. Okay. So what is our recursive case then? So these are all base cases, right? These are all base cases that we know enough, having seen these inputs, to fully solve the problem we're trying to solve, right? To determine whether or not these two lists are equal to one another. Well, what other case remains? Well, one case that remains is, if we imagine this stage of solving the problem where you have two nodes whose data values are equal, but you don't know what comes after, right? And we're going to leave that part to recursion as we've just previously discussed. So our recursive case is going to be is equal. And 110 is going to be the first node that comes in, and 110 is going to be the first node of the second list that comes in. And what does this result in? Well, this is where we use the beauty of recursion to say, you know what, we've seen enough at this step, but recursively, the algorithm can go process the next node of each list and decide whether it's seen enough or it's going to be lazy and say, oh, recursion, you go solve the rest of it. So how would this look with recursion? So we would take the next of each of these, right? So this would result in is equal. And I'm just going to write, if we call this A and we call this B, A.next and B.next, right? And this is how we're going to move forward in lockstep through each of our lists, node by node by node. We're going to do that recursively, okay? So we've identified 4 base cases here that maybe we could use some complex logic to condense down into 2 related base cases. So any of these or one. But before we worry about that, I think it's going to make sense to try and just implement what we've got here. And then if you wanted to, you could go and clean up this logic on your own afterwards. Okay. So from the previous video, we also had set up exercise 6 with our linked list starting point. And if you don't have this file, you can grab it from the course site. And if you're just following along, just pause the video here and set up this file. But otherwise, let's go ahead and start working on our skeleton for this particular function, right? So what does our skeleton look like? We're going to have a function named is equal. And the is equal function is going to be given, say, a list named A, which will be a node, and a list named an optional node, because we might have an empty list here, right? So an optional node, and B will also be an optional node. And this is a function that is ultimately going to return true or false, whether or not these two lists are equal to one another, right? And so the language we'll use to describe this is are A and B equal, right? So this is a predicate function that will return either true or false, okay? So if we refer to our notes, we can see, okay, here are base cases, and let's just solve the easiest one first. If both are none, then this is true, right? So if A is none and B is none, then return true, right? Elif, all right, let's go back to our list of notes. The next case is the first node is not none or has some value, and the second node is none, right? And one of the ways that we can test this is, well, we know that if both were none in this very first case, right? So we can be a little bit clever here. We know that if both were none, then we've already returned from this function and we would never get to this elif. So at this point, if A is none, then we can return false. And actually, if I wanted to match the logic of the notes that we had, let's make this B, right? So what we're saying is if B is none, if the second parameter is none, then we can return false because the first node isn't none. Otherwise, the very first case of our if statement would have been reached, right? And we can do the same thing for the other side. So elif A is none, we can return false. And then there was another elif that was if a.data is not equal to b.data, right? Return false. And so these are our 4 base cases that we enumerated and trying to think through what are the simplest problems we can solve in working towards the solution, right? We started from the easiest cases and then we worked towards, well, okay, we at this point, we know they both A and B are nodes and they must be equal to each other at this point. And this is where the logic takes a little bit of, may take a moment to become comfortable with, right? If A's data is not equal to B's data, then we would return false and we would never go on and check, the next else case. Else, right? And I might make a note of this. A.data and B.data are equal, right? And so else, we've reached what is like, these are the cases that we know how to solve this problem given the data we've seen so far. We've seen enough at this point. But this else branch is, well, we haven't seen enough. So let's go solve the rest of this problem using recursion. Otherwise, return is equal a.next and b.next. And that's our recursive step. And notice that we fully addressed all our base cases first, and then we left the rest of the problem to the beauty and seeming magic of recursion. But as you know, there's no magic here at all. We're just making another function call and moving closer and closer towards one of our base cases, right? Now, I mentioned that we could simplify our logic a little bit. One of the places that you might simplify is, elif B is none or A is none, right? This is another place where we could have had this in one condition. So I could have said if A is none or B is none, and we would have left those just the same. So if either of those cases is, if either of them are none, but the other is not, after having checked whether they both are not or are none, allows us to simplify that case a little bit. But you could leave them individually, right? We're expressing the same logic here. And then the last elif is testing for their data not being equal to one another, meaning we've still got 2 nodes in each of these lists. We haven't made it to the ends of either, but one of them's data is not equal to the other, right? And lastly, well, let's leave the rest to recursion, okay? So we could test this out really quickly by starting up a REPL. And we're going to, from exercises.exo6.linked list, which is where I stored this, we're going to import. And I'm going to use the star here because we've got our function and our node class. And so we could ask, is equal none and none. This is one of our base cases. And we know that that's true, right? Empty list is equal to the empty list. That's fine. Is equal node of 110, none, and none. That's false. We could test the other case where we had none first and node of 110 followed by none, right? And I have too many parentheses. That's also false. And we could test is equal node of 110, none, and node of 210, none. And of course, these 2 lists should not be equal, and that's false. Well, what about a case where they are equal? So node of 110 and none, and node of 110 followed by none, right? And that's true. You might be wondering, well, why didn't we return true when 2 nodes were equal to one another? And the reason is, yeah, this is great in this case, but what if we had something like, node of 0 followed by node of 110 followed by none, and node of 0 followed by 110. And let's make this 111 followed by none. And I think I need one more parenthesis here. That's false, even though the first two nodes were equal to one another, right? So when you're looking at two nodes, just because they're equal isn't enough. We need to make it all the way to the end of both, which means that we've checked whether or not every prior set of nodes was equal to one another, or pair of nodes. And only once we've made it to the end of both can we be certain that these two lists are in fact equal to one another. I would encourage you to play around with this a little bit even further. And this is a great function to practice diagramming if you'd like to trace the recursive function calls there. So once again, we applied this strategy of starting with the simplest problems possible. And this sort of feels like starting from the back of a problem and from like the edge cases of a problem that are the simplest for you to solve. And importantly, knowing that you can solve them immediately without any recursion, without any looping or anything like that directly, like you know the answer just by looking at the arguments you're given. And these are going to form your base cases. And then from there, you're hoping to, once you run out of the different possibilities for your base cases, you're going to be looking for, well, how can I make my problem just slightly more challenging such that I can use a recursive step to solve the rest and apply this process recursively to the rest of my problem. Great work.